But it is also mentioned that the minimum Reynolds number is should be 10 to the power 5. So corresponding to the Reynolds number D minimum, the minimum Reynolds number should be corresponding to the minimum flow rate, right? Because Reynolds number is proportional to velocity, which is proportional to flow rate. So the minimum Reynolds number should correspond to minimum flow rate. So the minimum Reynolds number, the critical Reynolds number should correspond to Q dot mean or the corresponding mass flow rate, M dot mean. M dot mean is basically rho into Q dot mean. So the minimum mass flow rate should correspond to minimum volume flow rate. So we can write down that your Reynolds number, so let's say your M dot mean is basically rho into the volume flow rate is the velocity mean times area. Area of cross section of the tube is pi d square by 4. So it says that determine the size of the orifice plate such that the pipe Reynolds number is not less than 10 to the power 5. That means the minimum Reynolds number should be 10 to the power 5. Therefore, there has to be a minimum velocity, and you have to find the corresponding tube diameter D. Okay. So now, so the Reynolds number RED in the critical minimum Reynolds number is basically 10 to the power 5. Okay. So what is Reynolds number? Reynolds number is basically velocity. So this is mean. So that is velocity minimum into D over the kinematic viscosity, nu. So that means your V mean should be Reynolds number D mean into kinematic viscosity divided by diameter. Okay. So we can now write down. So the minimum flow rate is 0.3 kg per second. So M dot mean is rho into V mean. So in place of V mean, we will substitute RED, Reynolds number minimum, nu over D into pi d square over 4. Okay. So that gives you so this is basically the M dot mean is 0.3 kg per second, right? 0.3 kg per second. On the right hand side, we have rho into nu pi by 4 into D, because this D this square get cancelled. So we have pi rho nu D divided by 4 into RE diameter minimum, right? So before proceeding, we need to know the properties. Okay. So we have to know what is the kinematic viscosity, what is the density before we proceed further, because everything else is known. So here we have pi by 4 into Reynolds number minimum is given, which is 10 to the power 5, into rho nu into D. D is something we are asked to find. We need to find out these two properties. So what is that we know? We know that the pressure is 5 bar, that is 5 into 10 to the power 5 Pascal. We also know the temperature T1 is 25 degrees centigrade, which is 298 Kelvin. So corresponding to this condition, we can actually find density of air just by using this ideal gas equation, R into T1. So 1 refers to the upstream pressure trap, and that is where the flow is coming. So pressure is 5 into 10 to the power 5. Universal gas constant is 287 into 298 is the temperature. So this is the gas constant of air. And then, so if you do the calculation, you get this as 5.846 kg per meter cube. And if you know rho, the dynamic viscosity of air at 25 degrees C, the dynamic viscosity mu from the table, you can read this as 8.41 to 10 to the power minus 6 kg per meter second. So you can find out kinematic viscosity as mu over rho. This will come out to be 3.15 into 10 to the power minus 6 meters square per second. So you know both the properties now, and you can substitute here. So 0.3 will be equal to 5 by 4 into 10 to the power 5 into rho. Rho is 5.846. Nu is 3.15 into 10 to the minus 6 into D. So now if you find out D will come out to be 0.207 meter. So in order to have a minimum Reynolds number 10 to the power 5, the minimum size of the diameter is basically 0.207 meter. Okay, so now knowing D, we can actually find out what is the orifice diameter, because beta is given. So beta is given as 0.6, which is basically D by D. And so this is basically 0.6 equal to D by 0.207. So the orifice plate diameter D is basically 0.124 meter. Okay, so that is the first part of the question. It says that an orifice plate with a corner tubs is to be used to measure flow rate of air at 5 bar and 25 degrees centigrade. The maximum flow rate is given, the minimum flow rate is given, but the question is asking determine the size of the orifice plate such that pipe Reynolds number is not less than 10 to the 5. When it is saying not less than 10 to the 5, this should be the minimum. So in that case, you should be considering the minimum flow rate condition and find out the tube diameter and then correspondingly the orifice diameter, because the ratio is known. Okay, beta, which is the ratio of the two, is known. The second part of the question is calculate the differential pressure across the orifice plate. So you have pressure tab 1, you have pressure tab 2 there, and you are asked to find delta P. So for that purpose, we can use this formula that we had studied in the class that said the mass flow rate is flow coefficient times the area into 2 rho into delta P square root. This is the formula that is there in the PPT. So if we rearrange the term, we can write that delta P is equal to flow coefficient. So delta P will be basically.
So delta P by 2 rho, if I'm not wrong. 2 delta P by rho. Oh, that is the formula. Sorry. M dot is equal to.
Just 1 second. If I do that. See, let me check the units. This is meter square, kg per meter cube. This is Newton per meter square, so kg. Mass into acceleration 1 over meter square. So if I do, so this is meter square, kg meter square. So kg per second. This is correct. This formula is correct. Okay. So this delta P is supposed to be 1 over 2 rho. So if I square it, then you have m dot over Ka square. Okay. So if I substitute the values, so that will be 1 over 2. In density, we have found 5.846. 5.846. M dot is 0.3 kg per second. And area is pi into the orifice area of cross section, 0.124 square divided by 4, pi d square by 4. So 4 goes to the numerator into K. So this K we do not know. So there are two ways we can find out K. Either we can use the Stall's equation that we had discussed in the class, okay, which has a relatively long expression. I would write down the Stall's equation here. So this says, so that will give you the CD, not for the flow coefficient. If I ask this question, I will actually give you the flow coefficient value. But here we had gone through this plot in the class, which relates flow coefficient K with Reynolds number. So it will have a value something like from 0.6 to 0.8. And depending on the value of beta, these curves will go something like this. Okay, so let's say this is beta equal to 0.75. This is beta equal to 0.5. And let's say this is beta equal to 0.6. So corresponding to the Reynolds number of 10 to the power 5, from the plot, the flow coefficient K comes out to be 0.652. Okay, so I will provide this value if I ask a question. So this K is 0.65. So if I do the calculation, I get this as 124.9 Pascal. Okay, so that is the delta P across the orifice plate. Okay. Now you can also find out, see, the question said that calculate the differential pressure developed across the orifice plate. So you have found out the delta P corresponding to the minimum mass flow rate. So this delta P should be minimum. But you can also have delta P maximum. Okay. So delta P max similarly will be 1 over 2 rho m dot max K square. Only difference is that instead of 0.3, you do use 1 kg per second as the maximum flow rate. And this will come out to be 1392.4 Pascal. Okay. So you need to have a manometer which should be able to measure this high a pressure. Okay. So this differential pressure will have two values, delta P min and delta P max, corresponding to the minimum and maximum pressures. Okay, so if there is no question here, I would move on to the next question.
Yes, sir. Yes, sir. Please.
So the next question is about a rotameter. And this rotameter is to be used to measure air flow rate at 7 bar and 21 degrees centigrade. So I hope you all remember the concept of rotameter. So we had a tube which is tapered, and initially we have a bulb which basically is sitting down here, and there is no flow. And depending on the flow, the bulb basically goes to some position. And so this tube is tapered. So this taper angle is alpha. And this the final position of the bulb is a balance between the drag force, the weight, and the buoyancy force, right? And we equated these three, and we found out the velocity and corresponding flow rate for a rotameter case. So the question says a rotameter is to be used to measure airflow at 7 bar. Okay, so the pressure is 7 bar, that is 7 into 10 to the power 5 Pascal. And temperature is 21 degrees centigrade, that is to 90, 94 Kelvin, right? The maximum flow rate is given. M dot max is 0.0005 kg per second. The inlet diameter of the rotameter is 8 millimeters. So here, the diameter here at the bottom, I think it is D naught, is 8 millimeter. The length of the meter is limited to 10 centimeter. Okay, so your L max, the maximum length can be 10 centimeter, which is 10 into 10 to the power minus 2 meter. That is 0.1 meter. The bob is constructed such that it has a frontal diameter of 8 millimeter. Okay, so the diameter of the bob is 8 into 10 to the power minus 3 meter. And the volume of the bob is 2.5 milliliter. That is 2.5 into 10 to the power minus 3 liters, so minus 6 meter cube. 1 milliliter is 10 to the minus 3 liter, and 1 liter is 10 to the power minus 3 meter cube. So you get 2.5 into the minus 6 meter cube. Determine the taper of the tube. So that means you are asked to find what is the alpha, taper angle. The shape of the bob is chosen such that the drag coefficient is constant. The CD is 0.8. The density of the bob material, rho B, is 50 kg per meter cube. So you are only asked to find alpha. So what formula do we have? We derived in the class that the flow rate is proportional to the displacement of the bob, how far the bob goes up. And this constant of proportionality K is expressed as follows: 2 into BV into G over the coefficient CD into SB into density of the bob minus density of the fluid divided by density of the fluid into pi d tan alpha. Okay, so we need to the fluid is air. We need to first know what is the density of the fluid from the property, from the pressure and temperature condition. Because volume of the bob is known, this is G is anyway known, the drag coefficient CD is known, the diameter of the bob is known, so the frontal area is known, right? And density of the bob is known. This the diameter here, so this is not the minimum diameter is same as the bob diameter, so D is known, that is basically 8 millimeter. This is known. We are asked to find tan alpha. Before that, we need to know what is rho F. So we need to find the density of the fluid as pressure of the fluid divided by R into temperature of the fluid. That is from the gas law, right? Ideal gas equation. P equal to rho RT. 7 into 10 to the power 5 is the pressure. R is 287 and temperature TF is 294. So if you do the calculation correctly, you get 8.406 kg per meter cube is the density of the fluid. So here all the parameters are known. So you can write down tan alpha. If you just readjust the terms, it will be K divided by pi d into 2 VG CD SB into square root. So you substitute all the values that we know. K is so this K we do not know, but we know that Q is K into Y. That we know.
So
now,
what is K?
Sorry?
So what does the K count?
K is a constant of proportionality that relates flow rate with the displacement of the verb. Okay. And that K is basically expressed as this, if you follow whatever we had covered. But from this condition, you can find out K value. Although K is related to this, but you do not know alpha. So you cannot determine K from here, but you can determine K from here because you know the mass flow rate. So you know the volume flow rate because you know the density. And you know the maximum position of the bulb, that is L max, you know. So from there, you can actually find K. So let's say the maximum flow rate is 0.005 kg per second, right? So m dot, so your K is Q dot divided by Y. In the limiting case, we have m dot over rho into Y. And in the limiting case, we are taking m dot max divided by rho. In this Y is basically L max. So if you substitute all the values that we know, this is 0.0005 as we have noted down here. And density is 8.406. L max is 0.1 meter. So if you do the calculation, K will come out to be 0.000595 meters square per second. Now that K you will use here, 0.000595 divided by pi. D is given 8 millimeter, 0.008, right? Into 2, volume of the bulb is given 2.5 into 10 to the power minus 6 meter cube, as we have noted down here. And that is into 9.81 divided by CD. CD is given, the drag coefficient is given 0.8. The frontal area SB is basically pi into d square by 4, that is pi into 0.008 square by 4. That will come out to be 5.207 into 10 to the minus 5 meter square. So that is substitute here. That, because these things will be under the square root, into density of the bulb is given 50 kg per meter cube, right here. Rho B is 50, rho F is 8.406. So if you do this calculation, this will come out to be 0.00964. So that means alpha will be tan inverse 0.00964. That will be equal to 0.55 degree. So the taper angle is nearly half a degree. Okay. Okay, so if there is no question, I would move to the next question here. So we have a pitot static tube. So I hope you all remember what is a pitot static tube. There is a difference between pitot tube and pitot static tube. Pitot tube measures static pressure. So pitot static tube measures static pressure. There's a difference between static pressure and stagnation pressure. So pitot tube measures static pressure, whereas pitot static tube would measure the stagnation pressure. So typically, if you have a tube here and if you create a hole, something like this, and you connect a U-tube manometer, right? So this will give you the static pressure. Now, if you have a tube and you insert a pitot tube, typically it is pointed, there is a small hole through which the manometer liquid is placed here, and so this pressure will be the stagnation pressure. Okay, because the velocity here, the flow is in this direction. The pressure measurement happens in the normal direction. So the fluid molecules here do not come to rest. But here, at that point, the kinetic energy and potential energy both are converted into the pressure energy. Okay, so in addition to the pressure energy, you have the kinetic energy that is converted to some kind of potential energy, and that appear in the form of pressure. So you get a higher pressure measured here, that is known as stagnation pressure. Now, what is a pitot static tube? So this is called pitot tube. A pitot static tube will have So which is again connected to U2 manometer. The thing is, here you measure stagnation pressure, but there is an opening here which would basically measure static pressure. Because here the flow is in this direction, the pressure is getting measured, the opening is in this direction. So the fluid molecules here do not come to rest. So whatever pressure you measure here, that gives you the static pressure. But here the fluid molecules come to rest, so that gives you stagnation pressure. So this is the Pitot static tube. So this is the difference between Pitot tube and Pitot static tube. Pitot tube measures static pressure, Pitot static tube measures stagnation pressure. So the question is, the Pitot static tube is used to measure velocity of an aircraft. If the air temperature and pressure are 5 degrees centigrade and 90 kilopascal respectively, what is the aircraft velocity in kilometer per hour if the differential pressure is 250 millimeter water column? Okay. So let me just correct this. I did not draw this properly. So in fact, this is connected to one arm of a U-tube manometer, and the stagnation pressure is connected to the other arm of the. So basically, this side you have static pressure, this side you have stagnation pressure. The difference between the two gives you the dynamic pressure. So P stagnation pressure, P static pressure is half rho m minus rho this is just simply the kinetic energy, which will be half into, so this will just be the V square by 2G. Okay, so this is the kinetic dynamic pressure head, this is the static pressure head. So here in this question, using a Pitot static tube, if you want to measure, the formula comes out to be V equal to 2 into rho m minus rho over rho into G into H square. Okay, so basically from here we get this formula because this pressure difference is measured in terms of the height difference in the manometric liquid, and that is expressed as here. So now, what are the things that we know here? We know that air temperature and pressure we know. So we need to find air density. This is basically density of the medium, or in this case it is air. So this density of air will be the pressure of air R into the temperature of air. Pressure of air is 90 kilopascal, that is 90 into 10 to the 3. R is 287. Temperature is 5 degree, that is 278 Kelvin. So that will give you 1.128 kg per meter cube. So the other thing we want to know is this the delta P here, this is basically the delta P across the manometer. Okay. So this delta P is rho m minus rho a into G into H, which is density of the manometer liquid so we are saying that it's okay if the air temperature is what is. So it says that it is water. So if the manometer liquid is water, then we take the density of water, which is 9998 minus the density of air, which is 1.128 into 9.81. The differential pressure height is 250 millimeter, that is 0.25 meter. So you can find the delta P across the manometer here to be 2446.8 Pascal. So you know this delta P, so your V is basically 2 into delta P over rho square root. So you can substitute 2 into 2446.8 divided by 1.1 1.128 square root. This will come out to be 65.87 meter per second. So this is what was asked. Okay, a Peters static tube is used to measure velocity of an air. If the air temperature and pressure are this, what is the aircraft velocity in kilometer per hour? So this is in meter per second. So you can convert into kilometer per hour. That is 65.87 into 18 by 5 will give you kilometer per hour. That is basically 237.1 kilometer per hour. But this formula, the application of this formula is based on certain assumption. That assumption is that flow is incompressible. That means your Mach number should be less than 0.3. So if the Mach number is greater than 0.3, you cannot apply this formula. You have to use another formula that is giving in the text. Okay. Taking the compressibility into account. So once you calculate the velocity, you need to check for the Mach number. So to calculate the Mach number is basically velocity of the aircraft divided by velocity of sound in the medium. And what is velocity of sound is expressed as gamma into pressure over rho square root. So gamma is basically the specific heat ratio, which is for air, it is taken as 1.4. Pressure is given as 90 to 3, 90 kilopascal. Rho is 1.128 kg per meter cube. So if you find speed of sound in that condition, this is 334.2 meter per second. So if you calculate Mach number, it is 65.87 V divided by 334.2, which is coming to be 0.197. So it is indeed less than 0.3. So that is incompressible flow. That means whatever we have calculated, the velocity of the aircraft is actually correct.
So only one query.
Yeah.
If you go up a bit.
Yeah.
P static is equal to PS plus V square upon 2G.
Mhm.
Is that half into rho into V square? I'm sorry if I
Okay,
missed
rho
something.
is missing because, yeah, correct. These are
Exactly.
Newton per meter square. Yes, rho is missing.
Thank you, sir.
So this is Newton per meter square, right? So there has to be rho there. Yeah, correct. Okay, so I think I would stop here. It's almost time. Again, in this chapter also, I would encourage you to solve more questions so that you get more practice. So we'll again we have I think one more week, right? We discussed that I will only take
Yes, sir. Next 3 classes you were telling.
Recording stopped.
yes. So we discussed that I would not be taking classes for the last week. So 30th is your exam, if
Yes,
I'm
sir.
not wrong, right? So we'll have
Yes, sir.
3 classes, and I have to cover. We have to solve some questions based on this miscellaneous property measurement, and I think we should be able to complete in the next week. So did you get in touch with code office regarding your difficulties that you had in the NSEM exam? Hopefully this time things get
We have expressed everything to the course coordinator Manivannan, sir.
okay.
So for INSEM it will be in the TCS campus now, sir. So
Yeah. If it is a TCS, I think things will be better.
so question paper will be hard copy now, sir. They will circulate to us now, sir.
I think the details I do not know. I have done
Okay.
my job. I have already sent a question paper to them.
Right,
So
sir. Right, sir.
I exactly do not know. You are going to write on paper, right?
Yes, sir. That is what whether IT team will give the paper or we have to bring. I will get it.
Yeah, those details, please, talk to either the course
Code office.
coordinator or the code office.
Sure, sir. I will get it to you.
Yeah.
Okay.
Okay, thank you all, and
Thank
we
you,
will
sir.
meet again Monday. Okay.
Thank you,
Yes,
sir.
sir.
Thank you, sir.
Thank you so much.
Thank you so much, sir.
Thank you.
Yeah, thank you, Professor, sir.
Thank you, sir.